So I'm continuing transformational geometry in this video. Just to pick up where we left off, a note about dilations, which I didn't mention, is that dilations create similar figures, which you might have already guessed. So the corresponding sides are in proportion and corresponding angles are congruent. Again, dilations are not always rigid motion since they do not always preserve distance or congruency. So continuing from there, I want to discuss a little bit composition of transformations, which I talked about a little bit when talking about rotations, thinking of larger rotations as just multiple smaller rotations. So something to note is that let's say that you call R rotations are determined by R, and you do like X degree in the subscript as so that's a rotation by X degrees. And let's say that I should say AB is a translation A to right, B up. A units to right, B up. Then if I did, so that's just like I'm just explaining the notation. Now if I did R X degrees, this little symbol, which means of TAB, this is a composition. It's a composition of a rotation and a translation. The thing is, even though normally we read left to right, when you see this, you're going to want to work right to left. So basically, I have some XY. The first thing I do is translate it by AB. So XY goes to X plus A, Y plus B. Then once I have this translated points and a figure is just made up of a bunch of points, if I do this to all the points in the figure, then I rotate it by X degrees. And that's how you get the overall transformation that is this composition. So really important, a little tricky, remember to read right to left. Work, read right to left in compositions. And of course, some compositions, it doesn't matter if you work right to left or left to right. They're commutative, but not all. For example, rotation and translation are not usually commutative. Two rotations are, for example, what I was saying before, rotating 270 degrees is the same as rotating 90 degrees 3 times. So, that would be rotating 180 degrees and then 90 degrees, or rotating 90 degrees and then 180 degrees. So continuing on, what are some types of composition transformations? Well, composition of two reflections across two parallel lines is equivalent to a translation. So let's draw two parallel lines to kind of see what we mean by this. So we have lines L1 and L2. Pretend that they're perfectly straight and parallel. And first, I have this point, XY. So first I'm going to rotate it across, reflect it across the parallel line L1. So I'm imagining folding the paper along the line L1 and rotate it to here. And then I want to rotate this across L2. Now I'm imagining folding the paper across the line L2. And it goes to here. Oh, I wanted this to be in red. Well, that's just a translation. If I let this be B and that be A will be negative, of course, in this case. That's a translation. Now, composition of two reflections over two intersecting lines is equivalent to a rotation. So again, I'm going to draw L1, L2. Here's L1. Let me redraw that. Here's L2. I'm going to start with this point, XY. First, I want to reflect it across L1. So imagining folding the paper along the line L1. It's going to end up around here. Now I want to reflect this across L2. So again, imagining folding the paper along L2. More like this. It's going to end up around here. But if I wanted to get from the green to the red, I could just rotate it. And the rotation would be centered at the point of intersection. And now we're going to go over the rotational symmetry theorem. And after this, we're going to do a couple of worked examples, which will be a little more interesting, I'm sure. Rotational symmetry theorem. I'm just going to write it out and explain it. So it states that a regular polygon with n sides, so an n-gon, always has rotational symmetry. With rotations in increments equal to its central angle of 360 degrees over n. Rotational symmetry is commonly referred as mapping the figure onto itself. So let's work with a hexagon. Now we imagine if we rotate the hexagon by, well, hexagon has 6 sides first of all, so the degrees that we're working with are 360 over 6, which is 60 degrees. So the central angles, of course, are 60 degrees. So if I rotate this by 60 degrees, then this side is going to go there, and the other sides, I'll just shift one over. It's going to be the same. That's why it has rotational symmetry. That's what it's saying. Similarly, if I have this little triangle, well, this is 3 sides. So in this one, we're working with 360 degrees over 3 equals 120 degrees. So if I rotate by, this was rotate by 60 degrees. If I rotate this by 120 degrees, then this side will become that side. So rotating, so again, the rotational symmetry theorem states that if we have a regular n-gon, a regular polygon with n sides, then rotating by an angle equivalent to 360 degrees divided by the number of sides um, means that you'll get like the same image. So that's rotational symmetry. Okay, so now I'm going to do a couple of examples. And these are examples that I took from previous Regency exams. So they should be very representative of what you're likely to see on the regions. So the first one states that these two triangles, ABC and DEF. And we're told that ABC is congruent to DEF. That's what that little symbol, the squiggly line with the equal sign underneath means. And they want us to describe a series of rigid motions that maps triangle ABC onto DEF. Well, first of all, thinking about this, so we don't have it that all of the points in the new triangle go to the same quadrant, for example. So a rotation might not be the best idea. But we see that because A corresponds to D, a simple translation won't work. Yes, a translation should be involved, but a simple translation is not going to cut it. What I like to do is sometimes I like to work specifically with the coordinates. So, for example, A corresponds to the coordinate -3, 3, and D corresponds to the coordinate 3, 1. Well, one thing that immediately jumps out to me is that the x-coordinate of A is the negative of the x-coordinate of D. Is this the same for all of them? Well, B corresponds to E. Those have the same x-coordinates as A and D, respectively, so yes. And then C corresponds to F. Um, the C coordinate is 1, 2, 3, -7, 5, and the F coordinate is 7, -2. Okay, so how do I get so that the well, what not even how do I get? I know that part of it is that xy, we want the x to become -x. Um -x. Uh but then what about okay, but so yeah, so that's an intermediary step. So what I just did is I reflected across the y-axis. So let's draw this intermediary step. Here, I'll write it out in green. So the first thing I said is reflect across y-axis. So the triangle that comes from this intermediary step is, this would be, let's call it A prime. This would be, let's call it B prime. And this would be C prime. Okay, now how do I get from this prime triangle to the desired triangle DEF? Well, look, oh, whoops, sorry. Looking at it, I see that it's flipped. So there's gonna be another reflection involved, and I can infer the flip, the axis of reflection. It's this line, which is line y equals 2. So, and then I reflect 2, reflect across y equals 2. Um, so how I would represent that um, in the coordinates is, let's see if I can remember how to do this properly. So again, we're calling it xy. If we're going to reflect across the line y equals 2, well, what we would do is the x coordinates don't change. The y coordinates, first I'm going to subtract them by 2. I'm sorry. Oh yeah, I'm going to subtract them by 2. I'm going to negate that, and then I'm going to add 2 again. And that should reflect across the line y equals 2. Let me just check that that works as I wanted it. So let me try this point, -3, -2, the transformation that I just described, it would be -3, -2, -2 plus 2, which is -3, -4 plus 2, which is -3 comma 6. If I wanted to reflect this across the line y equals 2, I'd go up 1, 2, 3, 4 units, and then I'd go up 1, 2, 3, 4 units again. It actually happened to be B. That was non-intentional, and I would get -3, 6, which is exactly what I wanted. Not that we actually needed this whole like describe it in terms of x, y. I just think it's effective. So overall, the translation would be -x, negative quantity 5 minus 2 plus 2. So that's what it is. But what they're saying, what all they ask for is describe a series of rigid motions that maps ABC onto DEF. It would be this 1 and 2. And it actually doesn't matter what order you do because reflection is commutative. That's not always the case, but in this one it is. So reflect across y-axis and then reflect across the line y equals 2. And we're done for that question. Now, the second question is very similar. So in this one, we have triangle ABC is congruent to this triangle STU. And again, they want to know the rigid body transformations which produce the new triangle. So just going to repeat the process that I did before. So I'm going to work with coordinate B this time. Coordinate B is -1, -2, -3, -4, 2. That's the coordinates of coordinate B. From the congruency statement, we know that B, the corresponding point in the other triangle, is T, and that point is -2, -4. Well, immediately we see that what's happening is that xy goes to -y, -x. Is that the same for all of the coordinates? Let's check. A is -2, 5, and the corresponding point in the other triangle is S, and that is -1, -2, -3, -4, -5, -2. Yeah, oh wait. Oh, sorry, xy goes to -yx. But that's the same for those two. Let's check that it's the same for the last one, C. So C, the coordinate, is -4, 6. And the corresponding coordinate in the other triangle is U, and that coordinate is -6, -4. Yeah, so that seems to be it. Now, what is this -yx? Well, if we remember from before, this is a rotation by 90 degrees. It's good to specify the direction in when you're answering, so counterclockwise. That is the standard, but I can imagine them taking off points if you don't specify counterclockwise. Rotation by 90 degrees counterclockwise. Oh, wait. If I rotate by 90 degrees counterclockwise, xy goes to -yx, which is what I wanted. Okay, yeah, sorry. Sorry, and then the last thing is that they want you to specify about the origin. So again, similar to how like counterclockwise is the standard direction, about the origin is the standard reference for rotation, but you should specify in your answer that it's about the origin. And that's just the complete response, rotation by 90 degrees counterclockwise about the origin. And that's how we get from ABC to STU. Then one last example I want to go over is kind of going over to trying to go into going over that tricky idea of dilation not always being like a rigid body of motion. So this question said that triangle A prime, B prime, and C, A prime, B prime, C prime, is the image of triangle ABC after dilation with a scale factor of 1/2 and centered at point A. Is triangle ABC congruent to triangle A prime, B prime, C prime? Explain. Well, why don't we give, sometimes it's a good idea to just give numbers um, to, to the abstract question. So let's create this triangle ABC, and I'm just going to, sorry, want straight line. I'm just going to assume it's an equilateral triangle, so all the angles are 60 degrees, 60 degrees, of course, and let's just make the sides 5. Now A prime B, oh, sorry, I actually want to make the sides an even number, so I'm going to make them 10. Now A prime B prime C prime is the image after dilation with a scale factor of 1/2. So remember, dilation means that xy goes to kx, ky, where k is, I didn't say this before, but it's the scale factor. So in this case, xy goes to 1/2 x, 1/2 y. Well, it's centered at point A, so A should kind of like, A is kind of the fixed point, and then A prime is the same. A prime is the same as, here, let me do it in a different color. It's at the same place as A. And then B, instead of going out 10 units, will only go out 5. And C, instead of going out 10 units, it will only go out 5. And that's C prime and B prime. And so that's the triangle A prime, B prime, C prime. And that's what it means when it's saying it's centered at point A. It's kind of like A prime and A coincide. Now, is triangle ABC congruent to triangle A prime, B prime, C prime? Well, looking at it immediately, we see that it's not. There's no way to cut out triangle ABC and just turn it around and manipulate it so that it will overlay A prime, B prime, C prime. No, ABC is not congruent. Maybe I'll just write this out. Is not congruent to A prime, B prime, C prime because distances, or I should say distances, or let me explain that. Segment lengths, the sides of the triangle, are not preserved by the dilation. And so segment lengths, sides of the triangle, my goodness, my handwriting, sides of the triangle, distances, which the idea of distances that came up in the definition of rigid body motion. Yeah, so that's it. So you would say no, they're not congruent because just looking at it, it's not like you can overlay them. They're not congruent. They have the same angle measurements, but there's no side, angle, angle thing that we can prove congruency with. So those are just 3 regions types questions for now, and that's going to be the end of transformational geometry.